A warm welcome to everybody to another webinar about force sensors. Today we're going to talk about piezo force sensors and how to specify them and how to read the datasheet, which is not that easy as it sounds like. My name is Martin Betschart. I'm the product manager for force sensors in the Kistler group. The content today is as follows. We focus first, or the focus of the whole WebEx seminar is the piezoelectric one-component force sensor. First, I'll show you the basic design of the sensor, which is pretty important to understand the following topics. Then we're talking about reading the datasheet with some definitions that, in my opinion, need some explanations. And I will talk about the concept of preload as well, which goes into those definitions. Another main topic today will be the limiting bending moment. I'll show you the effect of a bending moment on the sensor, the consequences of it, and the resulting allowed working area of a sensor. So at the end of the day, you are able to define the optimal point of operation of your sensor, or you find out that you need another sensor, a bigger one or a small one. First, let me give you an overview about the force sensors within the portfolio of Kistler. You can see here we have one component force sensors, so-called load washers, and we have three component force sensors. Today we focus on one component force sensors, by the way. Both type of sensors are available already preloaded as force links. Preloaded means ready to measure, and calibrated. So you buy it, you install it, and you measure without any other issues that you face. Other sensors, we have strange sensors as well, of course, and we have 3-component and 6-component dynamometers, which are not within the scope of this presentation as well. So the focus today is the one-component force sensor as a load washer. As an example of a one-component force sensor, let me introduce you here the type series 9001A to 9071A of Kistler. As you can see, the design is in form of a ring. This is the generic form for piezo force sensors. And we have various types available, of course, but the basic principle behind it is always the same. You can see it here on the right bottom part. We have a number 1, the bottom plate, and we have number 2, the top plate. In between, there are 2 quartz layers, 2 quartz rings, which generate a charge as soon as they are loaded with a force Fz that you can see here. Precondition for a good signal, of course, is a perfect surface, not only when installing the sensor, but inside the sensor as well. And as usual, perfection is not achievable, so there are some micro gaps and so on within the sensor, which leads to a certain behavior, which will be the topic of the next few slides. The quartz crystal itself has a linear behavior when you apply force. That means you apply 1 force, you get 1 charge. If you apply 3 force, you get 3 charge. But at the lower force ranges, you have those imperfections leading to a non-linearity, just slightly, but still there it is. And in order to overcome this non-linear range of, we say, around 20%, you need to have a preload. That means it's better to measure in the nominal range of 20 to 100% than from 0 on. Some producers, they recommend to apply just 10%, which is also feasible here, but still, to be on the safe side and to have really a linear signal, it's better to go a little bit above these 10%. So we decided at Kistler to take 20% because we just have the best results there and the best experiences made with our customers. This nonlinear range in the lower force range of a sensor leads to a little bit confusing datasheet entry, which has a differentiation between a measuring range and a calibrated range. As you can see here, we have a measuring range of 7.5 kilonewtons or 15 kilonewtons, depending on the sensor. And this measuring range is the maximum applicable force, usually called nominal force as well. But since we recommend our customers and everybody to apply a preload to it, we perform the calibration with this preload as well in order to give the customer some values that he can enter into his charge amplifiers that are more accurate than taking the nonlinear part into this calibration range. Graphically, it looks like that nominal force is 100% of the maximum, or is 100% of the applicable force. And usually we reduce 20% applied by a preload and calibrate the measuring range above, which is a compressive measuring range. The preload itself is a static force that is applied to overcome macro gaps and small imperfections, as I mentioned before, and as a result reduces the effective measuring range. This is something you have to keep in mind if you define a sensor or you are looking for the most suitable sensor for your application. On the other side, it is improving the linearity by factors, not only 1 or 2%, but really by factors. And as mentioned before, we apply 20% of typical preload to such a sensor. Just a remark about preload and pretension. Preload is something different than a pretension, because at the preload you apply a force on the sensor and like putting a weight on it or something, and that leads to the force flux which goes completely through the quartz crystals within the sensor. A pretension, on the other side, is applied by a bolt, where you tighten the bolt and squeeze the sensor between a bottom and a top plate. This is the normal way of overcome these 20% of nonlinearity when a customer has an application and so on. But as a side effect, you have a force shunt that reduces the sensitivity of about 7 to 10% compared to the calibration sheet. This is not an issue, the sensitivity is still high enough, but you have to be aware of it, since on the sticker of the box where the sensor is delivered, you have different ranges of sensitivity which have a difference of these 7 to 10%, and that's why. The most common measurement of force is usually pressure force. So in order to be able to measure tensile force with a quartz crystal, since you are not able to pull such a crystal and inverse the effect of generating charge, you have to go another way, and that way is that you apply a higher pretension to the sensor. And this higher pretension allows a relief of the sensor and therefore measuring negative. Kistler is providing some pretension sets. You can check out the web page which one is most suitable for you. But as a generic rule of thumb, we say 50% of preload is best, because then the rigidity and the stability of the sensor is at an optimum point. One of the biggest advantages of a piezoelectric force sensor is its ability to survive overload. We define in the datasheet an overload of typically 20%. That means we allow 120% of nominal force and guarantee that there is no damage at all. However, we recommend to maybe calibrate it again, because it might be that the behavior has been changing slightly if you overload it several times. Now to sum up everything, let's go back again to an overview. We were talking about the nominal force, which is the maximum measuring range that you can see here on the left. We allow 20% of overload, what you can see here in red on the left side. We were talking about measuring range of the compressive force, which is the nominal force minus the preload. And we were talking about the measuring range of tensile forces, which depends on the amount of preload that is applied to the sensor. Just a remark to the datasheet as such, it is always a good idea to read the footnotes, because the preload is only recommended and not really visible there on the sheet. And one important thing is that the sensitivity, linearity, and hysteresis, etc., they are evaluated or calibrated in this case with a preload. Well, but the customer usually uses a pretension, means a force shunt with such a pretension volt. So it's always a good idea to do a calibration on site as soon as the whole thing is installed in order to verify your values. This is something that we can provide as a service from Kistler, that somebody comes on site and calibrates. But however, even if you have a calibration sheet, do a calibration on site. Again, this has not to be done in case you are ordering a force link, which is already pretensioned and calibrated with this pretension. And as a repetition again, calibration means we apply 20% of preload, and as a result, the calibration range is just 80% of the nominal force range from the datasheet. Now to a very important topic that has to be taken into account when dimensioning and specifying a force sensor, which is often forgotten and not that visible at all at first sight, which is the limiting moment. I'll show you here a service case from Kistler. We had a customer sending in a force link, which is a normal force sensor already preloaded, as I mentioned before. And this customer had an application where he tested a shock absorber. He applied 3 load cycles every 6 seconds to this force sensor. And the fault was, at the end of the day, the bolt got broken. Even though Fz, that means the applied force, was always within the limits of the datasheet. Now, the diagnosis of this fault was that the bending and torsional moment was repetitively above specification. There are certain countermeasures, of course, to take. You can take a bigger force link, which is more stable towards, or more rigid towards bending moments, or you control the movement of the shock absorber and build a tool guidance and prevent moments as such. Now, what's the problem of this bending moment? The bending moment adds an asymmetrical stress to the sensor, which is unfortunately not visible at all at the output of the sensor. So you can see here a normal force ring, which is built into a structure with a pretension bolt and a pretension force that you can see here in dark red, and you have a force that is applied by the process here in blue. On the right hand side you can see the stress that is distributed along the surface of the sensor, which adds up from the preload force and the process force together. Now, if you're not absolutely in line here with your force in the x-axis going through the center of the sensor, you apply a bending moment. You have a shear force here on the top, which generates an asymmetrical stress to the sensor that you can see here on this side. So the distribution of the force along the surface of the sensor is not given anymore, because On the left-hand side, you relieve the sensor, and on the other side, with the same amount of stress, you additionally add some stress to the surface of the sensor. As a summary, the bending moment has three main effects. The first one, the most important one, is it is invisible to the output signal. Whatever moment you apply, you add on one side the same force that you relieve on the other side, and if you add them together, you receive a blank zero on the output. Second point is the bursting limit. A bending moment adds some stress on one part of the sensor, and since you can't see it, you might go above the nominal load that is allowed for such a sensor, and you risk to damage it. You can see it here on the graph below, where we have two axes, force and moment. And as you can see, the more moment you have, the less force you're allowed to apply, or vice versa. That means the closer you come to the nominal force of your sensor with your process, the lower is the allowed bending moment. On the other side of the sensor, you relieve the surface from stress. And the risk there is, as soon as the bending moment stress, or the stress relief, so to say, is higher than the sum of the preload force or stress and the process force, you risk to lift off the measurement structure from the surface, and your measurement is not valid anymore because the force that is applied to the sensor is not distributed evenly anymore. You can see it here on the graph as well. That means the higher your force is that you apply, the higher the bending moment, or the negative stress from the bending moment, is allowed to be applied as well. What does that mean for our sensor? If you have a look at the graph below, we have two crossed lines. One is the lifting limit, the green one, and the other one is the bursting limit. So we have to stay underneath those two lines with our moment at any time. Of course, this area, this admitted working area, depends on the force that is applied. And if you have a look now where you are allowed to have the highest bending moment, it is at 50% of nominal load. You might remember that we said before, we try to give a preload to the force sensor where we are allowed to operate within this region. And here you can see the reason why. For those who might have a critical bending moment within their application, they are allowed, of course, to check out the user's manual, respectively the data sheet of the sensor. There you can see the exactly same triangle with some examples how to calculate it, and here you can see as well the formula for these two lines that are limiting the working area that is admitted for the bending moment. So just go to the datasheet of your sensor and check it out there. Having understood the basic concept of preload and the effect of a bending moment towards a piezoelectric sensor, we are now able to define the correct preload for an optimal point of operation, where the sensor withstands the highest bending moment and has the best linearity. On the graph on the left, you can see again the permitted working area in blue, minus the first 20%, which we defined before as an area where the sensor is not that linear. That's why we exclude it out of the permissible working area. That leaves us, in case of a sensor 9001A, a working area or a force range of 6 kilonewton. And if we choose to have a preload of 20%, we can measure the complete 6 kilonewton if needed. But in case you want to have a symmetrical point of operation where you are able to measure not only positive but also negative forces of the same value, you have to choose a preload of 60%. Then you can measure 3 kilonewton positive and 3 kilonewton negative. But keep in mind, as you can see here, when you go to the limit of 100%, then almost no bending moment is allowed anymore. So be careful there. Of course, as we said, one of the biggest advantage of a piezoelectric sensor is the overload capability. There is still some moment that is applicable in order not to destroy the sensor, but still this is a dangerous area to go to when you would like to reach 100% of the sensor. That's it from my side. Thanks for watching the video. I hope you enjoyed it and could take out some lesson learned, so you're a little bit closer to define your own sensor and which one you need for your purpose. In case you have some more questions or you would like to have some more information, visit us on www.kistler.com/. You will find there some more information about our sensors, or you might just drop an email and we get back to you as soon as possible. Thanks a lot and goodbye.